output voltage. Because let's say we were putting in 100 and we wanted 1 volt out, we'd have to run at what's called a 1% duty cycle. So that means the amount of time we're extracting energy from our inductor is going to be tiny compared to the amount we're putting in, and that's just generally going to give us a lot of problems. Finally, and most importantly, this circuit has no isolation, which is what we're going to take a look at now. So what is isolation? Well, it's absolutely crucial to the safety of modern appliances. And it boils down to the fact that the mains that we get out of a plug, so that's live here and neutral here, is not isolated. And what I mean by that is that where the power comes into your house, there's just 2 wires, a live and a neutral. There's no earth. Earth is created where the power comes into your house, where neutral is joined to the ground. We do this for several reasons, which maybe I can go into in another video, but the problem with it is it means that if you touch the live wire, you don't necessarily also have to be touching the neutral for current to flow. You just have to be stood on the ground, and current will flow through the ground and then back up to neutral. This is clearly very dangerous and is the reason why the output of our power supplies needs to be isolated. You're not going to find any power supply for anything, even from the dodgiest parts of the world, that aren't isolated. At least I hope. So essentially, isolation just means if we peer into the barrel jack of our DC power supply, we have our positive on the inside, we've got our negative on the outside, and there's no direct current path between either of them to ground. So our little friend could touch the negative, he could touch the positive. As long as he's not touching them both at the same time, he'll be fine. Also, in most cases, these power supplies are such low voltage, he can touch both at once and still be fine. So that's a quick look at isolation, but how do we realise this in a power supply? Let's take a look. First off, I'm sorry to break it to you, but an inductor is nothing special. It really is just a coil of wire, or in this case, several coils. The only thing that really makes them special at all is the fact that most of the time they're wound on some kind of ferrous core, and that's just to amplify and concentrate the magnetic field. So let's just draw our coil of wire. We've got our input, coil of wire, and an output. That's an inductor. Now, as I mentioned, we have a core, so let's draw some lines. So for low frequency inductors or transformers, this will typically be something to do with iron. Now, the important thing to remember is, whilst our energy is coming in through this wire and leaving through this wire, the energy is actually stored in the magnetic field in the core. So our energy is in here. And this means we can do something very clever. We can use this coil to put the energy into our core, but then, to get our isolation and the other things that we wanted, we can add a second coil. So it starts to look a bit like a transformer if you know what that looks like. But the crucial difference is that this is designed to store energy. A transformer is designed to transfer energy. So if I quickly replicate our voltages that we had before, this time on our primary, our voltage is going to come up. We're going to have 10 volts, and then it's going to go to 0 volts. What's happened to that minus 40 volts? Well, that's going to now appear on the secondary. And because this is a completely separate coil, what we can do is we can just flip it around to get rid of the negativity of the voltage before. So while the core's charging up from the primary, we're not getting anything out. And then, when we stop charging it, the energy is going to come out of our secondary, like this. And this is going to be our 40 volts. But what about my example before? What if we want a really big ratio between the two? Let's say our input is 110 volts. Well, we just put more turns on our primary. Again, just like a transformer. So by separating the input and output of our inductor, which makes it into a coupled inductor, we've solved all of our problems. Put energy in through the primary, take energy out through the secondary. Right, we're almost ready to start going through all the components and what they do. There's just one final thing I want to go over with inductors, and that's to do with their size. As you can see, this inductor on the oldest power supply is probably about twice the size of this one, and this new one is about a quarter of the size of that. Intuitively, the amount of energy an inductor can store is roughly proportional to its size, its volume. So if we shrink our inductor down, it can't store as much energy, which sounds like a bit of a party stopper, but there's one very simple solution. And let's take a look. So here we have 2 buckets. The yellow on the left represents the primary or input to our inductor, and the green on the right represents the output of our inductor, or the secondary winding. I have 2 inductors I can use, the big one and the small one. So first, let's use our big inductor. We're going to fill up the core with energy and dump it out onto the secondary winding. And we're going to repeat this process so that we get a constant power out of our power supply. Next, let's have a go with our smaller inductor. As you can see, it holds less energy, so to get the same power, the same total energy out in a given time, we have to scoop more often. Something worth noting is that we're leaking more. If you look on the floor between the two buckets, there's more water pouring out. Now let's compare the two together. As you can see, we're having to fill and empty our smaller inductor a lot faster, and this translates to a higher switching frequency. The switching frequency is how many times per second we're charging up and discharging our inductor, and this water leakage represents a few losses such as switching loss and core loss in our inductor. These losses are a fixed amount of energy that we lose every time we fill up our inductor with energy, so by doing that at a higher rate, it means we have more losses, and fundamentally that's what limits how fast our switching frequency can be. Right, now that we have a solid understanding of what's going on at the heart of our power supply, let's take a look at everything else. So, what I'm going to do to make this nice and digestible is I'm going to go from the mains AC input to our isolated DC output. And I'm going to start by going through the bare minimum components you'd need for this circuit to work. And then we're going to keep going through adding in new parts of the circuit. And I think you might be surprised at how simple it actually is. So first off, our power comes in here. We've got 3 pins, earth, neutral and live. As I've mentioned several times, this is AC, and the first thing we need to do is turn it to DC. So for that, we use this black component up here. This is a full bridge rectifier and contains 4 diodes in a special configuration to essentially get the negative part of our AC wave and flip it around so that it's always positive. Although this means our current is no longer alternating, I'm not sure we can call it direct because it's very up and down. To sort that, we then add a large capacitor, so that is what this thing is here. In this specific power supply, it's got a big sticker on that tells us the specs, but here are some other capacitors. Now, something very important to note about this capacitor that is true for all switch mode power supplies is that it is charged directly from the rectified mains, which in most of the world means you're going to be looking at about 350 volts on this capacitor, and they can hold their charge for days and weeks. So I'm not going to try and stop people from opening power supplies, in fact I encourage it, but make sure you have a multimeter, a resistor, some things to discharge this capacitor and check it is discharged, and no, your fingers don't count. Next we have a pair of components that work together. There's our inductor, which we already know everything there is to know about, and there's also our MOSFET, which is up here. So the T in MOSFET stands for transistor, and this is our electronic switch. This is what we use to connect the input winding of our inductor to this capacitor that we've charged up. So this MOSFET is directly used to control how much energy we put into our inductor. And in a simple topology like this, it's actually the only thing we control in the entire circuit. On the output side of our inductor, to take the energy out, we have a diode, and the diode's job is to stop energy from going into the output of our inductor. We want to turn on the MOSFET, that'll charge up the inductor, and then when we turn it off, the energy can only go out of our output through the diode, which is essentially an electronic one-way switch. And after it's been through this diode, it is then stored in these 4 capacitors. These are our output capacitors. And just like the input capacitor, their job is to smooth some very lumpy DC into some nice, smooth, clean DC. And that's it. The circuit would work, functional, and usable with just those components. So that means we actually understand how to build a power supply. We could do that ourselves. Please don't. But now, let's start going through some of the other components and see why they've been added. Surely they're not needed if it would work without them. First, and I think simplest to understand, we have an LED to show when the board is powered, and that also has an accompanying current limiting resistor to stop it blowing up. This LED just comes on when the output is on, so the LED being off doesn't necessarily mean that there's no AC on the input. It just means there's no DC on the output. Next up we have another inductor, which is this small inductor here. If you watched my previous video, you'll recognise this toroidal shape of inductor. And this is placed in the circuit after our DC output has passed through these 3 capacitors, and before it goes into this final output capacitor. This inductor, combined with a very small capacitor on the back of the board, acts to further filter and smooth our DC output, as large capacitors alone often struggle to remove all of the very harsh on and off signals present in these power supplies. Next we have 2 small resistors, again on the back of the board. These are placed across 2 of the output capacitors, and their job is to discharge the capacitors when the power supply gets turned off. This is just so that when you turn your power supply off, the DC output drops to nearly 0 volts within a few seconds, maybe a minute. And this is so that if the output got shorted or anything like that, you wouldn't get a big spark as all of these capacitors suddenly discharged into whatever had shorted it. The reason we don't need resistors like this on the big capacitor is because there's no direct connections from the outside onto this capacitor. In my opinion, this capacitor should still have a bleed resistor because it's still very dangerous, especially in open power supplies like this that aren't potted in a plastic enclosure. Next, we have yet another thing on the back. These 3 resistors. They are all very low resistance and wired in parallel, and the whole group of them is put in series with our MOSFET. What's the point of these? Well, these form what's known as a current shunt, and these are used to measure current. You may or may not have heard the equation V equals IR, which is telling us the voltage across a resistor, or set of resistors in this case, is equal to the current multiplied by the resistance. As we know the resistance, we can measure the voltage across these resistors to work out how much current is going through them. And this is used by the controller to monitor the current going through our inductor. Next, we're finally back to the front with this section, these 3 grey capacitors, and this special inductor. Together, these components form our input filter. Their primary purpose is to stop any of the high-frequency switching signals that come from our flyback circuit over here from making it out onto the mains and interfering with other products such as TVs. This inductor is known as a common mode choke, and as you can see from the schematic symbol, it's actually got 2 windings, one for the live and one for the neutral, and it actually looks very similar to our coupled inductor that we use for transferring our power, and that's because in construction it is almost identical. The idea of a common mode choke is that the polarity of the windings is configured in such a way that any noise that appears on both get cancelled out, but the mains AC that is going in the opposite direction in one than the other can pass through without being blocked. The grey capacitors are here because as the frequency across a capacitor increases, its impedance decreases. And essentially what that means is that they will soak up more energy from higher frequency signals. So with the 3 of these placed in parallel between live and neutral, they will absorb quite a lot of that high frequency switching noise that we don't want to get onto the mains, whilst having virtually no effect on the mains current, which is at 50 Hz instead of about 65 kHz that this circuit switches at. Next, in front of our input filtering, we have our input protection. This is here to protect the power supply from the mains if the mains does something dodgy, and protect the mains from the power supply if the power supply does something dodgy. First and foremost, we have this red thing, which is a fuse. I'm sure you all know what a fuse does, but if not, it's essentially a very thin piece of wire that's designed to be a lot thinner than all the other wires in the circuit, so that if too much current flows, this will break first. And because it's designed to break, it breaks in a safe way. Over here we have this large black disc. This is an NTC thermistor, and its job is to limit the inrush current, the current that flows when mains is first connected to the power supply, to charge up this big capacitor. An NTC thermistor has a high resistance until it heats up a bit, and then it drops. So when you first turn the power supply on, and the NTC thermistor is cold, its high resistance limits how much current can flow into this capacitor. Once the circuit's been running for a while, it's heated up, and its resistance has dropped, so that it doesn't really affect the circuit at all. Then down here we have this blue thing, which looks similar to the thermistor but quite a lot smaller. This is a MOV, or metal oxide varistor, and this is placed between live and neutral. A varistor is essentially a voltage-dependent resistor. So the bigger the voltage across a MOV, the lower its resistance is. This is designed to clamp spikes, and is one of the components you'd find in a typical mains surge protector. Big MOVs like this one are used to absorb energy from lightning strikes on large switchgear, and are quite beefy components. The final part of the input protection circuit is the 2 small resistors on the back. These are between live and neutral, and are mostly there to discharge the grey input filter capacitors. Because if you happen to unplug this power supply just at the peak of the AC wave, these capacitors could be charged up to the same voltage as this capacitor, maybe 350 volts. And unlike the big capacitor, these are before the rectifier, which means they are accessible on the mains input. So for that reason, we have more bleed resistors, just like the ones on the output, to ensure these are always discharged. Next, we have even more discs, these 2 blue capacitors. These are known as Class Y, or just Y capacitors, and these connect one of the inputs and one of the outputs of our rectifier to ground. As with the grey capacitors, these are mostly there for filtering, to prevent all the bad switching signals from getting out and interfering with other stuff, just by passing through the air, a bit like a radio. This interference is known as EMI, or electromagnetic interference. And we'll notice as we go along that quite a lot of these components are just here for EMC, which is electromagnetic compatibility. Basically, we have to make a lot of effort to make sure our circuit doesn't mess up other people's circuits. And it's a bit of a hassle, really. In our final step of adding bits, we've got a load of small components, mostly resistors and capacitors, and a single diode. These form circuits known as snubbers, and they are placed in parts of the circuit where spikes in voltage might occur. So we can see one on the input winding of our inductor, and that's because whilst most of our energy is stored in the core of the inductor and will come out the core through the secondary like we want it to do, some energy will unfortunately come out of the primary. And to prevent that energy producing a massive voltage like we saw at the very start of the video, we add this snubber circuit on. The snubber circuit across the output diode is there because when the diode is forward biased, so that means there's current flowing through our diode, everything is happy with the world. But then when we put a voltage across it the other way, and we expect it to block, there's going to be a period known as the reverse recovery time, when current actually flows in the wrong way through our diode. And again, this current can lead to a big voltage spike, so we put another snubber circuit across our diode. And finally, we add a very small capacitor across our MOSFET, and this is also to protect that from any potential voltage spikes. These snubbers serve two main purposes. First is to protect the devices they're connected to, and second is yet more EMC, as these voltage spikes can produce a lot of interference. Now there are still some other components on the board. Everything I haven't mentioned is to do with the control of the power supply. So for example, this black chip going from the input to the output is how the controller knows what the output voltage is. This little white circle is a potentiometer, so we can put a screwdriver in there and turn it to adjust our output voltage. But generally, we've gone over every component in this power supply, and we know what they all do. They all serve a purpose, even if that purpose is just to meet annoying EMC regulations. We made it. We now understand not only what is in here, but why it's there, and it only took us about 20 minutes. So please, if you liked the video, subscribe, it really means a lot. If I get enough requests, maybe I'll make some more videos about switch mode power supplies, such as going into a lot more detail about why this modern gallium nitride power supply can be so tiny. But until then, once again, thank you very much for watching. Goodbye.
Sponsored by Brilliant. This is not electricity. You can't see electricity, you can only see its effects, such as light, heat, motion, magnetic fields, very expensive bills, and electric arcs. Take this simple circuit with a battery, a switch, a lamp, and a wire connecting them all together. The battery is adding energy to the circuit, and the lamp is removing this, transforming it into light and heat. We can flip the switch to control this. What's happening is tiny particles called electrons are moving through the wire from the battery's negative terminal through the lamp and into the positive terminal. They actually move a very small distance, but I'll explain that in just a moment. Many of us were taught that electricity flows from the positive to the negative. That's because long ago, Benjamin Franklin theorized that electricity was an invisible fluid. He rubbed a glass rod with a cloth, which then gave him a shock. He believed the cloth was adding more of this fluid, making it positive, while the person touching it had less, which made them negative. So he assumed that electricity flowed from positive to negative. Schools then taught this information, many still do, and we call this conventional current. Some years later, Joseph Thomson experimented with a cathode ray tube, a device with two metal plates in a vacuum. When powered, a strange ray appeared, and it oddly traveled from the negative to the positive side. He observed that a magnetic field influenced the ray's direction. He also noticed that when passed between electrically charged plates, it deflected in the electric field between them towards the positive side. As we know, like charges repel and opposites attract. So the beam must be made of tiny particles with a negative charge that moves from negative to the positive. He called these particles an electron, and we call this electron flow. Unfortunately, Benjamin Franklin had guessed incorrectly. The cloth was removing electrons from the glass rod, and they were moving from the person to the rod. The common analogy is that the battery is like a pump, providing the pressure to push the current through the circuit. We measure this electrical pressure in the unit of volts. For example, this battery is rated to provide 1.5 volts, and this one is rated for 9 volts. The water flowing through the pipe is similar to the electrons flowing through the wires. We measure the flow rate in quantity per time, and we measure the current in amperes, or just amps. 1 amp is equal to 1 coulomb per second, which means that if 1 amp was flowing through this wire, then we would have 1 coulomb of charge per second passing this point. An experiment by Robert Millikan calculated the charge of an electron, which is a tiny number. But from that, we can calculate how many electrons are flowing, and we see that 1 amp is equal to around 6.2 quintillion electrons per second. So we just say 1 amp to make it easier. The lamp is adding resistance to the circuit, similar to a section of thin pipe, limiting how much water can flow. We measure the resistance in the unit of ohms. So the voltage is the pushing force, which moves the electrons, and the resistance makes it difficult, so it limits the amount of current which can flow. But we can use Ohm's law to calculate the resistance, voltage, or current in a circuit as long as we know 2 values. So if we measure the current in this circuit and we know the voltage, then we can easily calculate the resistance. From that, we can calculate how much energy is being consumed. By the way, I did make these handy mugs with all the formulas on, making it quick and easy to use. Links down below if you would like one. So where are these electrons coming from? Well, they are already in the wire, although some do come from the battery. The wire is typically made from copper, which is just a structure of many tiny copper atoms. Atoms are so small that this cubic centimeter of copper contains over 84 sextillion atoms. So this wire contains a lot more. An atom is just a collection of 3 particles: the electron, neutron, and proton. Different elements have different numbers of these particles. These elements are listed in the periodic table, and here we can see copper. I'm going to use the Bohr model to illustrate the atom, but some of you will be familiar with the more accurate quantum mechanics model of an atom. This is very complex and beyond this video, so we're going to use the Bohr model. This shows that the copper atom has 29 protons and 35 neutrons at the center, which forms the nucleus. It also has 29 electrons around the nucleus in different orbital shells. In the outermost valence shell, there is 1 electron, which is free to move around to other copper atoms. Due to ambient thermal energy, these electrons will naturally move around. They are mobile, and they move randomly in any and all directions. These mobile electrons are bouncing off of atoms and ending up roughly where they started. While some move left, some move right, so the average is 0. The electrons are negatively charged, and the protons are positively charged. Neutrons have no charge. When an electron leaves the atom, there are more protons, so it has a positive charge, and we call this an ion. The copper atoms are all sharing electrons, so inside the wire we have the same number of electrons and protons. Therefore it is balanced and no charge exists inside the wire. The protons are positively charged and their electric field lines point radially outwards, while electrons are negatively charged and their field lines point radially inwards. The field lines of 2 electrons or 2 protons will repel each other, but a proton and an electron will attract. If we connect a plate to each terminal of a battery, we would have a buildup of negative charge on one side and positive charge on the other side. If you imagine that these magnets are electrons and they are creating a neutral charge with their protons, when the battery adds an electron, it squeezes them, so the charge has increased. They only need to move a small amount for that to happen. We know that magnets can interact through their magnetic fields over a long distance without physical contact. The same with electric charges. Their electric field lines reach out across the gap. We can see that by applying a high voltage across these 2 plates. The grass seeds will align with the electric field, revealing the electric field lines. By the way, these arrows indicate the direction a positive charge would move. In our case, we use electrons which are negatively charged, so they move in the opposite way of the arrow, which is a little confusing, but just remember it moves from negative to positive. Our battery has a negatively and positively charged end, so it has an electric field. By connecting a wire, we can direct an electric field through the wire, which helps to move the electrons from the negative to the positive terminal. The electrons still move randomly, but the electric field causes them to drift towards the positive terminal. As they move together through the wire, they create a magnetic field around the wire. We can see that using some compasses. We use this to build electromagnets, and it's also used to drive electric motors. So how far do electrons move? Well, let's assume a current of 1 amp is flowing through this wire. We can calculate the drift speed, which is less than 0.1 millimeters per second, which means it would take a very long time to travel this small distance. But when I flip the switch, the light turns on. So how can electrons travel so slowly? If you imagine these are electrons, when we move an electron at one end, its influence travels much further and faster. In the wire, we have an initial pulse of electric and magnetic fields propagating down the wire at close to the speed of light. Then an electric field causes the electrons to drift because of the surface charges, and we'll see that in just a moment. If I take 1 meter of this resistive wire, the resistance gradually increases along the length of the wire. By the way, this is different to standard copper wire. We use it in things like toasters because the large resistance creates heat. Copper wires have almost no resistance. If we applied 10 volts across the ends, the voltage gradually reduces along the wire, but the current is the same at each point. That's because the magnitude of the electric field inside the wires is the same. So something is happening when we connect the wire to the battery. The battery contains a mixture of materials, specifically selected because they produce a chemical reaction which absorbs electrons on one side and ejects electrons on the other side. Imagine that the chemical reaction pulls in an electron and forces it to one end. Each time this happens, the electric field grows and makes it harder for another electron to move across. But the chemical reaction force is so strong that it keeps moving them until the forces become equal, and then it stops. If an electron leaves, the forces are unbalanced, so the chemical reaction forces another electron across to restore and maintain that balance. For me to move these magnets towards each other requires energy. They want to repel. For the chemical reaction to move this electron against the electric field also requires energy. For every coulomb of charge moved, it requires 1.5 joules of energy. That is our voltage, our electromotive force. This is the pressure the battery can provide. Other chemical reactions can provide different voltages. So, due to the chemical reaction, we therefore have a buildup of negatively charged electrons on one side, and the other side has a shortage of electrons, giving us effectively a positive and negative terminal. This charge at the ends of the battery is going to create its own electric field. Remember, our piece of resistive wire has a neutral charge inside because of the balance of protons and electrons. No electric field exists, and so no current flows. But when connected across a battery, the battery pushes electrons into one end and pulls them out of the other. So the buildup of charge at these terminals needs to transition from negative to positive along the length of this resistive wire, which forms a gradient of charge. The charge is on the surface of the wire. We can think of it like a ring. There are regions with higher concentrations near the battery, lower regions elsewhere, and a transition point where it flips from negative to positive. Imagine we took a disk of copper. The protons and mobile electrons are balanced, but if we added some electrons to the center, they repel the other electrons away, and they can only go as far as the surface. The charge at the center remains balanced, so the excess charge must accumulate at the surface. If we remove some electrons from the center, the remaining electrons have more space, and they expose some of the positive charge of the protons. This effectively gives us a positively charged ring. So at the transition point, we have a positive and negatively charged ring, and on the sides, we just have two rings which are both negative or both positive, but one is slightly less charged than the other. Whenever we have a difference in charge, we have an electric field which points from the more positive to the negative. So an electron in this field will be forced towards the less negatively charged region. If you imagine it takes energy to force these repelling charges together, the energy is stored in the field between them. We can use this to move other charges. The gradient of charge creates an electric field around the entire circuit, which forces the electrons to move. The energy is stored in a charge around the wires. This resistive wire is the same diameter and the same material, and the current is the same at each point. So the magnitude of the electric field must also be the same, which is caused by the surface charges. In a normal circuit, the wires have almost no resistance, and they are relatively thick compared to the thin wire of the lamp. The electrons are very easy to move through the copper wire, but it's very hard to move them through the thin lamp filament. So the surface charges mostly accumulate at the battery terminals and either side of the lamp filament, with very little gradient needed along the copper wire. Using a multimeter, we can see nearly the full battery voltage across the lamp, with only a small voltage drop along the wire. If you think about water passing through a hose, when we place our thumb over the end, we reduce the cross-sectional area, so the water flows faster through this part, even though the same quantity of water flows before and after this point. The same must happen with electrons in the filament of the lamp. The electric field is stronger because of the steeper surface charge gradient, and that causes a higher drift velocity. But the same quantity of electrons move, so we have the same current. We can look at the math behind that in my course where I have more time to explain this. Links down below for that if you're interested. But these electrons are going to collide with atoms in the filament and transfer their kinetic energy into the lattice. It's very difficult for the electrons to flow through, so it keeps happening. The electrons slow down, but the electric field keeps forcing them to move, and they collide again and again. With each collision, the filament becomes hotter and hotter, and eventually it becomes so hot that it emits visible light. Now, the circuit typically has a switch to control when current can flow through the lamp. The battery is usually already inserted, and the switch is on the positive side. That means that this section becomes negatively charged, and this section becomes positively charged. So we have an electric field around the wire, but not in the wire, so no current will flow. When the switch closes, some very complex interactions happen within a fraction of a second before the light fully turns on. I'm going to briefly explain what happens. When the switch closes, the charges along the face of the switch will meet and cancel out, leaving just the surface charge rings with strong opposite charges. This creates an electric field which moves an electron. As the electron approaches the positive ring, that ring becomes slightly less positive and the negative ring becomes slightly less negative. Electrons are starting to move, so a magnetic field is developing, and the change in surface charge creates an electric field. The disturbance affects the immediate neighboring sections, so the electric and magnetic fields travel like a wave down the wire in both directions. But other sections of the circuit are unaware of this change at this moment. The electric field reaches out across the gap and influences the surface charges elsewhere in the circuit, creating small disturbance waves and a tiny current here too. As these waves move along the wire, they will hit parts which cause partial reflection waves. These waves interact with other waves, and they help to establish the gradient of surface charges in the electric fields, which stabilizes the circuit, and the light eventually illuminates with a constant current flowing everywhere in the circuit. All of this happens the moment we flip the switch. The electrons move such a small distance that they can't carry the energy from the battery. It's the electric field in the wire that accelerates them to deliver the energy where needed, and this electric field is due to the surface charges along the wire. It can be difficult to understand electrical engineering topics and the math behind them, but our sponsor Brilliant is where you learn by doing. There's so many new courses, but I really enjoyed their new Vectors course. The graphics and interactions just made it so easy to visualize each step and there was extra help if I needed it. Brilliant has thousands of interactive lessons in math, data analysis, programming, and AI. All the skills you need to become a brilliant engineer. They even have an app for on-the-go learning, making it easy to build your critical thinking skills through problem solving, not memorizing. Each lesson is filled with hands-on problem solving that lets you play with concepts. I think you'll enjoy this too, so you can try everything Brilliant has to offer for free for 30 days. Just visit brilliant.org/The Engineering Mindset, or you can scan the QR code. You'll also get 20% off an annual premium subscription. Do check them out, links down below. Hey, I'd just like to give a huge shout out to our incredible Patreon and channel members. Thank you so much for supporting us. And if you'd like to see your name here, along with priority access to our content and behind the scenes footage, links down below for how to join.
In order to save money 3D printing this part myself for 85 cents, I spent $35,000 on this tooling.
Back in the grocery store. Free range, organic, and even that top term, pasture raised, the creme de la creme representation of the top shelf eggs. Once a time ago, these words used to mean something, represented higher quality, but in the year of our Lord and Savior
2026,
these words mean absolutely nothing.
One of these egg yolks is factory farmed. The other is pasture raised. Can you tell the difference? Probably the orange, right? Darker, richer orange color probably has a higher concentration of nutrients. Yeah, I guessed that one too, but I lied. Both of these eggs come from factory farms. Things have changed. You see, big factory farm companies got hip to the #1 indicator egg consumers would look for to see if the eggs they brought home were real or not. The color. When a chicken is caged, denied sunlight, given antibiotics, and fed a diet of only corn, they don't produce a good egg. Just like a mother notices her kid's face turns pale when they're going through illness, pale egg yolks or yellow egg yolks is the primary sign that the egg came from a factory farm. Or at least we thought that was the primary sign. You'll come to learn in this video that true pasture raising farmers don't actually have as much control over egg yolk color as you'd think. And although some savvy consumers may have thought that checking for egg color gave you the truth about your eggs, factory farm companies have figured out how to manipulate an egg yolk's color so that it passes the consumer eye test, and they maximize profit by marketing these eggs as top shelf quality, although they're actually a product of the very same conditions you're trying to avoid. Now, you're gonna get some street smarts in this video, like why you don't want fed a vegetarian diet written on your carton of eggs. But first, this photo. This is an egg yolk from the first carton of pasture raised eggs I've ever had. It was just a few years ago. I began to whip the yolk before I realized just how dark it was. So I quickly cracked an egg that was certified USDA organic into the same bowl to compare, and that's what brought you this picture. I didn't even know what I'd use this picture for at the time. I just knew it felt like I unlocked an industry secret. How is it that these USDA organic eggs don't even come close to the color of these true pasture raised eggs? Fast forward to today, and we are on a mission to reconnect back to real food, and it dawned on me that majority of Americans likely have never had an actual real egg, even those that think they have. In a recent survey sent out to 1,000 Americans, 86% of respondents purchased at least one product with animal welfare associated labels like pasture raised. Now, this isn't a survey of people's preferences. This is collecting data of people who spent their money in hopes of getting something they thought was worth it. Vital Farm eggs. These are the most premium top shelf eggs that you can buy at your local grocery store chain. They come in organic, pasture raised, I mean the whole nine. But more importantly, they're a tax write-off for this video because, Jesus Christ, these were expensive for what you're actually getting. They're expensive for what you're actually getting. This is the only brand that gives you a QR code that you can scan, be able to see the farm where these eggs were laid, which is pretty cool. But wait until you see the condition of the farm where these eggs were actually laid. Thanks to Element for sponsoring No Lab Coat Required and riding with the channel for so long. If you haven't hopped on an Element train yet, now's a great time. Element is a hydration drink mix that helps active individuals achieve an optimal hydration status. Vital electrolytes, sodium, potassium, magnesium are what power every nerve impulse, every jump, lift, squat, and dip. I use Element before, during, or after a workout to provide my body with key electrolytes that empower motion. Around this season, I enjoy Element in coffee, as coffee is proven to be a diuretic, so it tells the kidney to release sodium, so adding sodium back in keeps me in balance. Purified water provides H2O, but it neglects the very thing that ensures true water balance, and that is electrolytes that direct water to its designated area, potassium inside cells and sodium outside of cells. Shop Element below and get a free sample pack with their most popular flavors, even if you used my link before. I gotta warn you, this stuff is deliciously salty. I look forward to exercising, sweating, and then being able to replenish with Element. Chocolate is my go-to flavor in the colder months, but you can find your own favorite flavor using the link below. Thank you guys for visiting their site, and thank you Element for being a sponsor of No Lab Coat Required.
All right, back up. What does all these words mean anyway? Pasture raised, free range, cage free. What's the difference? My name is Johnny, but I'll be frank. Free range doesn't mean anything. Pasture raised means the birds were raised on pasture. I'll be frank. You didn't laugh, but somebody did.
You'll find pasture raised to be a highly regarded phrase in high quality livestock and poultry farming. When an animal is raised on pasture, something incredible happens that doesn't take place in a factory farm operation. Pigs love to roll in mud, cows like to jump and run, chickens like to peck and play. Sure, it's a wonderful sight to see farm animals doing farm animal stuff, but the beauty is that pasture raised gives your meat and eggs a more robust nutrition profile. You actually bring home a greater density of nutrients and get a greater return in every bite. It's real, healthy food. But here's where a lot of us get it mixed up. It's not necessarily the freedom of the animal under a pasture-raised system that actually determines its final nutrition quality. Big agribusiness and industrial farming has done an incredible job at hiding one simple truth. You see, we don't really get our vitamin A from carrots, and we don't really get our magnesium from kale. Even the egg that boasts of having every vitamin except C, even this is not the source of where we actually get our nutrients. This, what you're viewing, is responsible for all of your nutrition.
The glittering orbs and flashes of light are microbes feeding, reproducing, and dying.
These microbes are known as organic matter, and organic matter plays the most vital role in making nutrients available to us. I once made the mistake of calling this dirt, but no, this is soil. Now, why am I bringing this up? Because sometimes, you guys know me, I just like going into the foundation, the fundamental. I think understanding something at a level this deep can really grant us the ability to be able to be smarter people in the marketplace. Not to mention, this is the start of a system that chickens need to exist in. Let me explain. Organic matter makes nutrients available in the soil. Plants grow from the soil and inherit these nutrients. The chicken comes along, pluck, eats the plant. The chicken poops. Those nutrients return to the ground to begin a new cycle. But here's what's most important. The density of organic matter translates through each stage, meaning the more fertile the soil, the better the plant, the better the chicken, and the better the human. This is an egg layer concentrated animal feeding operation, or what we call a CAFO. In a typical egg layer CAFO, hens are situated on wire and plastic. They're propped up on concrete pads and routinely administered antibiotics to stave off the encroaching pressure of disease an environment like this creates. CAFOs withdraw from this natural cycle of ecology. Ecology, the study of living organisms related to one another. CAFOs dismiss the notion that living things need other living things. It treats the chicken not like an animal, a part of this ecological system, but as an egg machine whose only input is grain feed and antibiotics.
Why is this chicken moving like that? Better chill out.
And so it's aptly named factory farming. Okay, Johnny, I get it. You're just trying to scare me by telling me, you know, it's the old, do you know it's in a hot dog trick? No, not trying to scare you. First off, I like a good hot dog. Secondly, we just gotta stop getting fooled. And we have to understand the chasm of a difference between a pasture-raised product and what the CAFO environment spits out, because that difference is how the industrial agricultural industry is able to be sly and fool us by putting things like vegetarian fed on a carton. Let's talk about that. When chickens graze pasture, they eat grass, plants, and bugs, and more. There's obviously no access to plants in a CAFO, but that's only half of the problem. CAFOs are sterile environments. They're sanitized to prevent spread of disease. Even the chicken poop is virtually sterile because of the antibiotics the birds are given. Why is this important? What does this sterility mean? It means no bugs. So the chicken is deprived of the omnivorous diet their DNA expects and living in this sterile environment. But we just said it a second ago. In order to be a healthy human, we need things that come from or interact with a healthy, fertile soil. And so fertility and sterility are mutually exclusive in nature. No organic matter in a CAFO, no life. So vegetarian fed or fed a vegetarian diet, this is a marketing phrase, and it's not even a good one. It just plays on consumer ignorance because we don't know that chickens are omnivores. And we have some weird, strange association between vegetarian, that term, and it's just some positive association with it. I don't know why. It's like not the early 2000s anymore. Like, we good. We've learned so much. Eat meat. And so vegetarian fed is the first dead giveaway you're likely eating CAFO chicken. So what about nutrition? How different is the nutrition you get from a CAFO egg and a pasture-raised egg? In a CAFO environment, laid right out in front of the chicken is a buffet of grain, GMO grain that is. This study took 125 of the same breed of chicken and separated them into two groups to be raised in opposite environments. They caged one group and fed them the copy-paste diet of factory farm chicken. 55% corn, about 10% soybean, and the rest was all this stuff. This is your so-called vegetarian diet for the chicken. It's funny, this list kind of resembles a processed food ingredient list.
Because it is one.
3% wheat middlings though, is that so bad? You're about to find out. The other group of chickens were given a life of rotated pastures that was just grazed on by cows. These chickens had a dang good life. They do love some cow dung larvae.
That's cow poop with baby fly.
Put that rotated pasture word in your back pocket for later, because there's something important about that you should know. The results, these CAFO chicken egg layers actually beat the rotated pasture eggs in one area, and that was yield. The caged hens dropped 0.85 eggs a day on average over a 6-week span. The pasture raised 0.72 eggs a day on average. So do the math. About 35 eggs a bird in the cage-free system over the experimental period, about 30 for the pasture-raised birds. It's important to note, and I'm making a note on this because yield is like the only fun argument for CAFO chicken, but you should know it's not as straightforward as CAFO just makes more eggs and feeds more people. Chickens, for one, have variable egg laying rates in the span of their life. So in their peak season, a hen could be dropping 0.90 eggs a day regardless of the system.
Hey, who's on B-roll, B? This ain't a chicken. I'm pretty sure this is a duck.
And factory farms don't keep their chickens for as long as pasture-raised farms. So pasture-raised farm egg layers are laying eggs for a longer period of time. But regardless of yield, because we won't go too deep into it, we gotta wonder what's being sacrificed for this yield. Let's go over the nutritional difference between these two products. The conventional caged birds produced eggs coming in with about 2,100 units of vitamin A per 100 grams of egg yolk. Pasture-raised birds, 2,900 units of vitamin A. For vitamin E, it's a knockout round, with the amount of vitamin E doubling for the pasture-raised eggs. There is also twice as much EPA and DHA. These are your anti-inflammatory omega-3s. There is a boatload of research and papers that reflect this very same nutrient result between CAFO and pasture-raised. But your MVP nutrient are really these omega-3s. Our bodies are flooded with omega-3s opposing nutrient, omega-6, because it absolutely bombards our food system here in the US, primarily in the form of seed oils like corn oil or soybean oil. Rings a bell? Corn and soy, top 1 and 2 ingredients in the CAFO chicken feed. These two have practically no meaningful amount of omega-3s, especially corn. Why does this matter? Well, these two omega fats compete for each other in the body. So it is the proportion of these omega fats that we get from each food that actually matters. For example, most people hear omega-3 and they think what? Fish oil. Well, consider the fact that omega-3s from fish oil are actually secondhand omega-3s, as fish don't make omega-3s, yet they instead they source it from their diet, microalgae. And the same thing goes for our eggs. Chickens eat grass, and grass are rich in omega-3s that actually translate into the egg. So again, it's a secondhand source, but it's vital to potentially correcting our imbalance that we've been experiencing for years now of omega-6 to omega-3. Turns out that when we allow our farm animals to eat grass and eat their natural diet, it helps correct our imbalance. Now, these nutrient differences are a big deal, but I'm actually not even sure they're the most important thing, as science actually falls short to be able to measure what we call phytochemicals, right? These are secondary nutrients, what we call secondary metabolites. There's a vast network of these phytochemicals that come in the tens of thousands, but the special part is that we have no idea what they do. We can hardly even quantify it. When a chicken eats grass and then we eat the chicken's eggs, we don't have any idea what we're actually missing out on. And I argue that the realm of the unseen, is actually what's truly important here. Okay, let's talk about another thing on the egg carton, the USDA organic seal. This ensures the birds were given organic feed, right? Yes, feed grown without synthetic pesticides or any synthetic chemicals. And this seal also guarantees the birds, well, I shouldn't say guarantee, but this label should also say that the birds aren't giving any administration of antibiotics. Now, I'm not looking to intentionally sow seeds of doubt with the USDA organic symbol, that label. I actually put a lot of trust in it myself, but that's just me. The entire theme of this video, and I'm going to repeat it more than once, is to be able to communicate the reality of the market to Know Labs audience. I dug into the USDA's organic guidelines, and there's just a huge loophole. They have this have access to outdoors requirement. And what you'll find is that this is just being exploited by Big CAFO. Hint, hint, you'll be able to see this exploitation in action when we look at the condition of the farm where these eggs came from. The actual big shortcoming with USDA organic is that it doesn't guarantee pasture raising or that the chicken was actually given a diverse diet. So yeah, CAFO can be organic, but what's often taking place is that these birds are still given an improper mono diet of only grain, and regardless of how you spit it, organic grain is still grain. Now, I'm not gonna say the USDA organic label is another dead giveaway you're eating CAFO chicken, but I will say there aren't too many truly local organic pasture raising farmers that are opting in for the USDA organic label, especially as they've underwent and accepted a few loopholes certifying CAFO producers that aren't necessarily following consumer values. So there's that. I plugged egg yolk color into Science Direct and got a hefty return on what the science says about egg yolk coloring, but more importantly, appearing to the practices the CAFO industry does to get their eggs to become dark orange. So remember those phytochemicals I was blabbing about earlier? One of the most important ones are what we call carotenoids. A carotenoid is a fat-soluble nutrient that is also a pigment. I'm only detailing it's a fat-soluble nutrient because an egg is highly receptive to fat-soluble nutrients, meaning whatever a chicken eats that is fat soluble, it will likely translate into being in the egg. And the industry knows that. Guess what's abundant in carotenoids? Grass. So pasture raised, grazing chickens can produce a nice dark colored egg. Okay, so surely it makes sense for CAFO's factory farms to feed their chickens grass because it gives them the pigment they're looking for. They can market that. Yeah, I thought the same thing. Like, why not just give the factory farm chicken some grass, right? Turns out corn has carotenoids as well. The industry will be elated if they could have corn be what pigments the egg yolk. But it turns out that grass withers, right? The nutrients are lost when grass is cut after a while. It doesn't store or transport easily, so it's really just a processing nightmare.
And corn doesn't quite do the trick because the carotenoid concentration is just low. So what are they gonna do to market to consumers who check egg coloring? Turns out they spend a lot of money on studies to try to figure this out. I pulled out one of these studies and I'm gonna share it with you because I think you're gonna find it interesting.
This study took 168 chickens in a typical caged environment and fed them conventional chicken feed with either marigold extract, red pepper extract, or a combination of the two. They added another group that ate only conventional feed with no pigments, a control group. All groups given the pigment extracts absolutely dusted the control group on the DSM chart, a chart that measures egg color. The control group landed at about 5. The other groups
ranged from about 7 all the way to 10. And these are just the numbers that I pulled. There are a lot more studies that exemplify that with the use of red and yellow nutrient pigments, the industry has complete control over egg yolk color from DSM-1 up to 15.
So, factory farms found a way to feed chickens things that are high in carotenoid concentration, like marigold extract. But Johnny, the thing is, isn't a carotenoid one of those special phytochemicals you were talking about? It still adds nutrition to the egg, right, at the end of the day. Yes, you're right on technical level, but it's not enough to disqualify the effects of raising a chicken in the CAFO in the first place. It's basically it's polishing a turd. Plus, the addition of these carotenoids do nothing for all the other nutrients we talked about earlier, especially those MVP omega-3s. The age of the grass, the season of the grass, the breed of the grass. Grass ain't got breeds. What's the word I'm looking for? You guys Google it.
Help me out in the comments.
Grass's carotenoid concentration depends on so much. Out here in the Midwest, our pasture-raised eggs can be DSM-6 in the fall and DSM-11 in the summer because of the changes in sunlight. So if you're relying on egg color to tell you what you need to know about your eggs, you smart, you loyal. But unfortunately, you're no longer ahead of the game.
You've got to be lying to me, dog. There is no way. Wait. You're telling me a yellow pasture-raised egg can bring home more nutrition than a CAFO orange egg? Listen to this.
This study analyzed pasture-raised egg changes across different seasons. They state yolk color, a key quality attribute linked to carotenoid concentration, did not meet consumer expectations in the colder months. But here's the key point. Don't miss this. Although carotenoid levels were preserved.
Okay, so I have here with me a carton of premium pasture-raised Vital Farm eggs. Now I cracked these eggs open and they were orange. So I scanned the QR code and I pulled up the farm and I hereby expose the problem with pasture-raised claims in grocery stores. This ain't pasture. This is an ecological catastrophe. So here's a top-down view of what we're actually looking at. Factory farms, if you've never seen one in person, I recommend finding one and standing as close as the barbed wire gate allows you. They're humongous. They're ominously long. You can squeeze hundreds of thousands of birds in these joints. I want to say the one we're looking at is about the length of a football field. Might even be a little longer. Sometimes they come longer. This is completely denuded soil. I'm not even sure if this qualifies as pasture. On their box, and when you look on their site, you'll see that the hens are raised on rotated pastures. Check your back pocket. That's the rotated pasture word that we talked about earlier. You see, the best pastures are the ones that undergo a routine period of rest. A bunch of chicken feet and cow hooves trampling and pooping on soil stimulates and fertilizes the soil, but at some point, you gotta stop stepping on the grass to allow it to regenerate. Come back stronger and more nutritious for the animals. We let the chickens pamper the soil, then step off, let it grow, then return. That's rotated pasture. And this helps explain where we get the term regenerative farming from. Animals add more to the soil than take away. It's sustainable, it makes other animals healthier, including us, as we've seen. And then you got this. This behemoth is a fixed concrete building. Ain't nothing rotational or regenerative about this. Okay, now Johnny, how can farms get away with this? How can they put pasture raised on the box and still be basically a glorified CAFO? That's because of these doors. These little doors actually allow for a few of the hens to get out and actually experience some fresh air. Mind you, there's hundreds of thousands of chickens in here, and we're looking at maybe 100 are actually out on this land. Now, if you look at the door, there's a bunch of chickens blocking the exit, and chickens usually rush to green pastures. But as you can see, these chickens hardly want to come outside and don't want much to do with this drying land and this dead shrubbery. And you're probably already doing the math, but the chances of even one of the eggs in this 18 egg carton coming from a bird that actually touched the outdoors, I probably got a better chance playing a lottery. You see, pasture raised is not a regulated term, at least not in the same way that organic is. It's a voluntary term. Think of it like extra credit you do when you're in school. If a company wants to use the word on their box, they turn in additional paperwork that basically explains how their poultry is pasture raised. And that's it. There's no farm inspection or anything like that. Now, what about free range? When we think free range, we think healthy bird on healthy soil, but we're actually getting something a lot closer to what we're looking at here. And the cage-free term is even worse. You get cageless birds, but they don't even have these little trapdoors. There is no access to the outdoors at all. So let's get organized. Pasture raised is not meaningfully regulated, yet you still want to see and hear the word pasture when you're shopping, because although corporate chicken has basically captured the term, our local and organic farmers still use it. More on how to determine if your eggs are actually pasture raised or not in a bit here. But as for free range and cage free, these just about guarantee you the bird is not in a cage, so it's allowed locomotion. That's it. Otherwise, free range and cage free on your egg carton are basically dead giveaways. You're eating CAFO chicken.
And real quick, because there's all these different nuances, we're really in the weeds here. You got CAFO cage free, CAFO free range, CAFO organic, but really it's not about distinguishing these differences. It's about understanding that CAFO is doing everything they can to market to you. On the other side, you got a true pasture raising farmer who just gives you a carton of eggs and hardly markets it at all. If there's a right way to do something, there's a wrong way to do something. You either get eggs from a CAFO or you get eggs from a pasture raised farm. That's what this all boils down to. Now, I know